welcome back to the channel. Today we will be walking through a really interesting new paper called Continuous Thought Machines or CTMs. This paper was published by Sakana AI in May 2025 and it introduces a brand new way of thinking about how neural networks can actually think step by step instead of just giving an instant answers. Now this video is going to be a bit long, so please be prepared, but don't worry, I have explained everything in detail because honestly, without going line by line, it's very hard to understand the figures and images in this paper, and those images plays a major role in explaining how CTMs actually works. To make it easier for you, I have attached all the variables definitions right at the start of this video. So if at any point you are confused about the symbols or maths, you can look back at the quick glossary to understand what's going through. Also, at the end of the paper, all things are available. I hope this walkthrough helps you understand this paper, and of course, I hope you will enjoy it too. Today give an answer instantly. But what if a model could actually think, step by step, like our brains do? That's exactly what the continuous thought machines does. The problem with modern AI is that it ignores something crucial. That's time. Real neurons just not fire once. They oscillate, sync, and evolve over time. Standard deep learning models throws all away using simple activations like ReLU or GeLU. The CTM brings time back into the picture, and that changes everything. Now you will tell me, why should we care? Because with timing, neurons can develop richer behaviors, synchronize with each other, and even decide when to stop thinking. That means CTMs can adapt to compute, take just a few tricks for each problems, or keep thinking for harder ones. In short, it doesn't just answers, it reasons. Now, neural networks were inspired by the brain, but they were missing timing. Yeah, that timing was missing. Our brains just flip a switch, they pulse, sync, and change rhythm over time. Imagine a drummer in a band. That exact beat and timing are crucial for our music. But today's AI ignores that rhythm and just plays a single frozen note. This makes AI good at narrow tasks but bad at being flexible like humans. So, who can adapt quickly, use common sense, and explain their reasonings? That's why continuous thought machines was built. It brings timing back into AI. It gives every neuron a little memory of its past hits. Let's like each neuron have its own mini brain to process them, and then measures how neuron synchronizes, like checking if the band is in rhythm. This way, CTMs can actually think over several steps, stopping every for each problems or taking more time for hard ones. Let's understand this figure 1. This diagram is showing how brain thinks in steps. First, the model takes in information and mixes it together using a synapse model. Then, instead of forgetting, it keeps a short memory of past signals. Each neuron has its own tiny private brain, a neural-level model that decides what it should do next, producing post-activations. All those neuron outputs are saved into a history, and from that, the model checks how the neurons are moving together. That's the synchronization matrix. It doesn't use all pairs, just pick important ones, which from like latent representations. From this, the model either makes output guess or defines where to look next in the data. That's attention, we have all learned in the Transformers paper. Finally, this information is combined with the neural states, so the model can take the next step in real life. Think of like an orchestra. Each musician is like a neuron. Listen to their past notes, plays their part, and together their rhythm syncs it up to the guide to whole performance. Like that guide the whole performance. Now, let's look into this listing one. Okay, so what you are looking at here is the CTM's main recipe written in the code. Think of it like an instruction for how the model thinks step by step. Like let's go into it like in a plain English. First, the model uses a backbone, that's like ResNet, to turn raw data, say an image, into useful features by like using backbone feature encoder. Then it sets up the attention tool so it can decide which part of the data to look at. Next, the synapse model mixes signal behavior neurons like how students in a classroom whisper ideas to each other. Each neuron has its own little private beat. I explained it in earlier. The model then loops through several thought steps at each step. It asks attention, what should I look at? It looks at the data, like zooming in on the eyes of a cat in a picture. It updates the neuron signals. Then it stores this into a rolling memory, dropping the oldest nodes and keeping the newest. Each neuron's private brain turns its history into a new output. The model checks synchronization, basically which neuron are in sync with each other. And then finally, the synchronization is used in two ways. First, to make predictions and to decide whether to look next in the data. And that's the loop. The model keeps repeating this process. Look, update, sync, and predict. until it has thought enough times. At the end, it returns all the output from each step like a detective writing down guesses as they become more confident. Now, think of continuous thought machines like a brain that creates its own inner timeline. Each step in this timeline is called an internal tick. Basically, one extra thought step. Unlike normal models like RNN or transformers, which move step by step only when new data comes in, the CTMs can keep thinking even if the input is just a single image. For example, imagine looking at a maze picture. A normal model takes one look and answers, but CTMs can look again and again. Tick 1, tick 2, tick 3, refining and understanding each time. This makes it more flexible, interpretable, and closer to how real brains processes thoughts. Okay, so what are synapses in CTM? Think of them like the wires connecting neurons together. The job of synapse model is to mix signals from different neurons and also bring in fresh inputs from the outside input. This mixing produces something called pre-activations, kind of like draft version of what each neurons will say next. But neurons just don't look at one moment. They keep a short history, like remembering the last few words. Like an example, remembering the last few notes in a song. This history gives context to the neuron's next move. So synapse is equals to connections plus memory of the recent activity. From this equation 1, plain meaning, as you can see, A1 is the pre-activation at time. They come from function FO, which is a synapse model. It takes two things stuck together. ZT, the neuron states from last tick, and OT, that's the new input or attention from the data. Okay, so now imagine a student, that's a neuron, about answering a question, a quiz. So they mix what they already know in their head and new info from the teacher's hint. That's the OT. That mixture is their draft throughout. That's 80. Now, if a neuron last state was 80% dog and the new hint is fluffy ears, the synapse mixes them pre-activation 80 and gives 90% dog at 90. Now, the equation 2. Equation 2 is AD equals to A minus and all these things. So AD is the pre-activation history here, the last M drafts kept in a rolling window. Think of it as a FIFO notebook where the neuron writes down its last M thoughts. Let's give an example. Like a musician who remembers the last 5 notes played, so their next note makes sense in the rhythm. Now you got the point? So the big takeaway from equation 1 and equation 2 is synapse mix old state plus new info to draft thoughts and keep the sliding window of draft to keep a memory for context. This part is about how each neuron in the CTMs has its own little brain. Normally, in a neural network, all neurons share the same activation rule, like ReLU, that says if the input is positive, pass it, otherwise skip. But here, each neuron gets its own private mini-model, a tiny multi-layer perceptron. Writes its own weights, this means every neuron can learn its own unique way of reacting to the history. Think of it like an orchestra. Instead of every musician just following one simple rule, like play louder if you see a note, each musician has their own mini sheets of rules about when to play, how to change the tempo, or how to react if the last few beats were quiet. That lets the whole orchestra play way more complex music together. Now, each neuron in the CTMs doesn't just look at what's happening right now. It remembers the last M steps of what it saw, kind of like keeping the last few seconds of song in your head. Scientists found that remembering somewhere between 100 to 10 to 100 steps works well. Now, instead of all neurons using the same rule, every neuron has its own way. A small neural network that looks at its history and decides its next move. The math looks like this. Now, this just means the next stage of neuron comes from applying its private function GG to own recent history. Giving each neuron its own private rule makes the whole system more powerful, but it also means more parameters to train. After all neurons updates, their outputs are combined with attention, results, and passed backend, so the machines keep thinking step by step. Imagine a classroom where each student keeps notes of last 10 to 100 lessons. Instead of all students following the same study guide, each of them has personalized methods. To revise through notes and prepare their answers, it take much more efforts, but the class and a whole becomes smarter and more versatile. Yeah, you can say that. Now in listing 3, here the CTM is learning how differential neurons dance together. Each neuron produces signals in every thought, like every step, and It shows how we measure use the rhythm. We don't just check the two neurons were even a sync, we also add a decay factor, meaning recent signals can count more than old ones. This way, the model can decide if it should pay attention to what happened just now or what's been happening for a while. Once we have this syncage, we can squash them into a representation vector that uses for making predictions and guiding attention. Now, let's talk about the continuous thought machines interacts with the outside world. How it takes in inputs and produces outputs. Instead of looking just a single snapshot of the neurons at one moment, CTM looks at how the neurons are behaving over time. It collects all the past neural networks, all the activities, and into what is called post-activation history. Imagine writing down all the friends in a group chat and said across the last few minutes. That's whole log the history. Now, equation 1 is the post-activation history, y. Z1 equals to Z1 to ZT. This just means line up all the neurons outputs from tick 1 to tick t, and let's take an analogy. Line up all the neurons outputs from tick 1 to tick t and play all the notes like a playlist of all the notes an orchestra has played so far. Each column in one tick, each row is one instrument. Now, this synchronization matrix ST equals to ZT into ZTT AS belongs to RD into D. What this is? This creates a big square matrix that tells you which neurons are in sync with each other. High values means they move together over time. Now, this next equation, that's 6 and 7, output and queries. This is how CTMs turn synchronization into prediction, and this one is how decides whether to look at the next data. It's like two use of group rhythms. One decides the answer, and the other decides whether the spotlight should go next or not. Now this attention step is OT is the attention, Q is equals to Q1, and KVN equals to feature extractor. This uses the query from synchronization to look back into the data features, like shining a flashlight on a part of a painting based on a rhythm of the group. Now this is a time decay. Here CTM adds a forgetting factor for each neuron pair. So recent movements can count more than the older ones. Like in the time forecasting we use. CTMs makes a prediction at every thought step, not just at the end. That means at tick 1, tick 2, tick 3, up to tick t. The model is constantly guessing. So how do we train it? At each tick we compute two things. A normal loss, like cross entropy, which tells us how wrong the guess is, and a certainty score, which is simply 1 minus entropy. So lower entropy is more confident. Instead of only training on very fast tick, CTMs picks two important ticks. For example, one is best guess and the tick where it was most confident. Then we can average those two losses. This makes the model learn across the whole thought process, not just the end. The cool part, the naturally gives CTMs adaptive compute. For easy images, it can stop early when it's confident. For hard ones, it keeps thinking longer. Now, let's go on the listing 4. This piece of code is a loss function for CTM. Basically how the model teaches itself from mistakes. Imagine you are taking a multiple choice test. At each thought step, internally, you write down what you think the answer is. Some steps you are very confident, other times you are unsure. The CTM doesn't just check your final answer, it looks at both. The step where you were most confident and the step you were actually closest to correct. Then it averages the two. This way, the model learns to get better at being right and at knowing when it's sure. So now let's go on the next paper, it's experiments. Now the paper moves into the experiments, where they actually test the continuous thought machines or CTMs on lots of different tasks. The goal isn't just to slow raw accuracy, but to see what unique abilities emerge from CTM's design. Remember, CTM has two big ideas. Each neuron has its own little memory model, and the network uses synchronization of neurons. To test these, they run CTMs on many fonts. First, classic vision task like ImageNet to check perception and calibration. Then a 2D maze navigation task to see if it care plan and build an internal map. Then sorting numbers and parity check to test algorithm reasoning. And a QA task on MNIST data to check memory and symbolic manipulation. And finally, reinforcement learning environments to see if it can interact with the world step by step. Together, these experiments show whether grounding AI in neural timing really makes it more brain-like. So we will discuss all this in detail. Now, imagine you are building a new kind of student. Instead of just blurting the first answer, they look at the photo multiple times. That's what ImageNet do. Trying to solve a maze on a paper, that's a 2D maze, and practicing solving messy stack. These are all the examples that we are going to experiment now. So let's just switch to the next one. So okay, how does the CTM actually perform on a big real world task? The authors tested it on ImageNet 1K, which is basically the Olympics of image classification, over millions images across 1,000 different categories like cats, planes, toasters, etc. etc. Now, the CTM isn't trying to break records here. They admit it's not the state of art and accuracy. Instead, the point is to show that CTM can solve ImageNet in a completely new way, using neural dynamics instead of just static activations. So now with our ResNet 152 backbone, the CTM reached about 72.5% top 1 accuracy and almost 90% top 5 accuracy. That means if you give it an image, its very first guess is right 72% of the time and the correct label is in the top 5 guesses, 9 out of 10. Pretty solid for the first attempt of doing ImageNet. Yeah, it is. So with this brand new idea of neurons thinking over time, the paper highlights this is the first ever attempt to classify ImageNet using neuron synchronization and timing at the representation. Now, this figure shows how confident the CTMs get at its think for more steps. On the left, the model only needs about 4 ticks of thinking to make the prediction for 100 times 100% of the images if we are okay with a medium certainty level of 0.5. On the right, if we demand a higher certainty of 0.8, the model still needs to think longer, and it will only make predictions on about 80% of the images. In other words, the harder the confidence bar you set, the fewer examples the model feels ready to answer. Let's understand with an example. Imagine you are giving a multiple choice test. If you only need to be 50% sure, you can answer almost every question quickly, even after just glancing at once. But if the teacher says you can only answer when you are 80% sure, suddenly you will skip the trickier questions and you will spend more time thinking before answering. That's exactly what CTM is doing here. Now, this CTMs makes a predictor is basically showing how the CTMs get smarter the longer it thinks. Look at the panel A. As the number of internal ticks goes up, accuracy climbs like a student double checking their work before handling it. Around 15 ticks, it's better to use the model certainty to decide whether to trust, when to trust the model. Now panel B shows the most images reach high confidence pretty quickly, less than 10 ticks, while only tricky ones need more. And panel C proves when the CTM says it's 80% sure, it's right about 80% of the time. That's called good calibration, and it means we can actually trust its probabilities. Also, the figure 2 and 3 shows how CTM can actually decide when to stop thinking. Imagine doing a quiz. If you are already 80% sure of the answer, you stop. If you are less sure, you keep checking clues. That's what the CTM does when it's internal takes. With a lower certainty bar like 0.5, the model only needs around 4 to 20 thought steps to be confident on nearly all images. But if we raise the bar to 0.8, not every image reaches that level, so the model keeps thinking lower. This is called adaptive compute. It saves time on easy cases and spends more effort on hard ones. Let's look into the figure 3.8. Then compares how to make predictions. Instantly at every trick or by waiting until certainty build up, the results show that about 15 ticks, trusting certainty gives better accuracy than averaging everything. Now figure 3b shows most images hit high certainty quickly within 10 ticks, and figure 3c shows something really impressive. The CTM is well calibrated, meaning its confidence matches reality. That's rare for neural networks. Usually we need special text to fix calibration. Here it comes naturally from the thought process itself. Okay. Now this picture shows how each neuron in the CTM changes over time while it's thinking. Every colorful squiggly line is one neuron's activity across multiple thought steps. What's amazing is that the neurons don't all look the same. They show very different patterns. Some are smooth, some are wavy, and some are spiky. This diversity is important because the model uses the same patterns to figure out how neurons are moving together. That's what we call synchronization. In simple terms, these swigglies are the raw thoughts, rhythms of the model, and together they form foundation of how CTMs makes decisions. Think of it like a band rehearsal. Each musician plays their own rhythm. Some keep a steady beat, others add flourishes. At first, it might sound messy, But the important part is how the rhythms line up when they all play together. That alignment is synchronization, is what makes music. And in the CTMs, the neurons' wavy squigglies are the rhythms, and the synchronization is how the model makes music to solve a problem. Now, this figure shows how the CTM doesn't just guess once, it follows a process. On the left, you see the model's attention map. Each one is like a heat map showing where the model is looking at, different steps. Over 50 thought steps, its attention shifts smoothly. First look at one part, then another, just like how our eyes move across a picture. In that top example, the CTM is very confident early on. It quickly locks onto the hockey players and keeps its certainty high. In the bottom examples, the model starts off unsure. We are looking at the tools. But as it keeps thinking, its certain curve rises until it finally gets the right answer. This shows CTM doesn't just spit out the answer, it reasons step by step, becoming more confident as it goes. Now, let's give it an example. Think of it as like a detective looking at the crime scene photo. First, she looks at the background, then the faces, then the objects in their hand. With each glance, she becomes more certain of what's happening. That's exactly what the CTM works. Its attention shifts across the images and the confidence grows as it pieces everything together. Now, here's something cool, really cool. Figure 6 shows what the neurons inside the CTMs are doing while it thinks about an image. Each dot here is a neuron, and each its color shows how active it is. Blue means quiet, red means very active. The CTM's neurons are arranged using a tool called UMAP, which basically swishes high dimensional activity down into 2D, so we can see it. As time goes on, each snapshot is one internal tick. You can literally watch waves of activity moving across the neurons. That's ripples, like a rippling spreading in a pond if you throw a stone in that. And that's the amazing part. Nobody told the model to do this. These traveling waves patterns just emerge naturally in the CTM neurons. That's exactly what happens in biological brains too. Scientists have measured low frequency traveling waves in the cortex that helps communication. Here, the CTM rediscovers a similar behavior on its own. Now, let's switch on a real-time analogy to understand this. Like a stadium wave as a football game. Each fan is a neuron, stands up and sits down in a rhythm. Over time, you see a wave moving around a stadium. That's what's happening here. Neurons are syncing upon in moving patterns. Now, let's talk about mazes. Imagine you are dropping into a big 2D maze. To solve it, you need to plan a path from the red start dot to the green finish dot. A normal AI might just color each pixel as path and not path. Kind of like filling a box without really thinking. But the CTM is different. It doesn't just spit out the final answer, it thinks step by step, choosing actions like left, right, up and down, wait. That forces it to build an internal map of the maze as it goes. And to make it harder, the researchers removed positional hints, so the model can't just cheat by knowing coordinates, it has to actually form a mental picture of the maze, just like a person would be navigating. Now, this figure compares three kinds of models trying to solve mazes: a simple feed-forward networks, a classic LSTM, and a new CTM. What you see is that the feed-forward network and the LSTM models either memorize badly or get stuck after a few steps. The CTMs, on the other hand, learns the full path and can solve much longer mazes. In figure 7a, the CTM's accuracy climbs all the way to nearly 100%, while the others stay flat. In 7b, as maze path gets longer, LSTM crash after about 20 steps, but CTMs keeps going strong. The cool part is CTM isn't just good because it has more parameters. It's good because it's a special design. Neurons with private memory and synchronization that makes it easier to train and better AI actually thinks through the maze. Now, figure 8 shows how the CTM is trying to solve mazes. Imagine you are tracing a path through a maze with your finger. Instead of jumping straight to the exit, you move step by step, keeping track of where you have been or planned ahead. That's exactly what CTM does. In part A, it follows the correct route all the way to the end. In part B, even when the path is longer than what is practiced in training, the CTM keeps tracing along correctly when we let it think for more steps than usual. This means it didn't just measure solution, it actually learned a general way to solve mazes, kind of like how humans imagine future moves while navigating. The paper even calls this episodic future thinking, the same way we humans the next step before we make them. When you're solving a maze on paper, at each step you decide, I'm here, where should I look next? That's exactly what CTM does mathematically. The attention query is the way of picking the next square to explore. Now, here the researchers tested whether CTMs could solve mazes that were longer or bigger than the ones it trained on. Think of it like practicing in a small playground maze and then being dropped into a huge corn maze. For the 39 cross 39 mazes it was trained on, the CTM could keep restating its path from where it left off until it reached the end, almost like picking yourself up at the checkpoint. It did that nearly perfectly, no matter how long the path. But when they tried much bigger tasks like 99 cross 99 mazes, performance dropped. Why? Because the start and the end are farther apart, and the CTMs wasn't trained for those distances. Still, the model shows it could stretch beyond training, hinting it was learning a general problem solved method, not just memorizing. That's pretty powerful. The trick is reapplication step. After 75 ticks, if the maze isn't done, they restart the CTMs from the point it reached. Now, like a video game checkpoint system, if you can only walk 100 steps before resetting, you just start again from the last save stopped, like where you have until finish the whole maze actually. Okay, here is basically showing how the CTMs get started. Imagine you are playing a video game maze. If you only react to walls as you bump into them, you will get stuck a lot. But if you build a mental map of the maze, remembering where the dead ends are, where you have already been, and where the goal is, you can plan your moves. That's what scientists call world model. It's your brain way of storing the structure and rules of the world, so you can reason, plan, and predict what happens next. A cognitive map is the part of the world's model that tells you about space, where things are, and how to get from A to B. Without a world model, an agent can only react, like a robot that just avoids the walls in front of it, without even realizing the whole maze exists. CTMs, by using its neuron-level models and synchronization, can actually build this kind of internal map. That's why, in their 2D maze experiment, CTM didn't just find quick tricks, it planned full routes through the maze, even without being told what pixels were on the ground. Now, let's look on the CTM's performance on CIFAR 10, a classical dataset of 60,000 small images across 10 classes like airplanes, cats, and trucks. Here the authors compare CTMs to humans, a simple feed-forward baseline and an LSTM baseline. Now let's understand this. Let's crack it out training curves in this figure 10. The gray line is the feed-forward baseline. It shows up quickly, reaching high training accuracy early, but it generalizes poorly with only 84% test accuracy. The red line is the LSTM. It's less stable, wiggly during training, but reaches 85.5 test accuracy. And the blue line is the CTM. Notice how it climbs steady and smooth, more stable than this LSTM. At the end, the CTM achieves the best accuracy score, that's its 86.0%. Now, let's look into 10B. Accuracy isn't the whole story though. What's really interesting is calibration. How will a model's confidence matches really? Figure 10b shows calibration plots. The dashed black diagonal is perfect calibration. If a model says 70% confident, it should be right about 70% of the time. Humans show up gray, are actually poorly calibrated on the task. They tend to be underconfident. The LSTM follows the same human underconfidence. The CTM show in red is much closer to the diagonal. In fact, it's better calibrated than both human and other models. So the big key takeaway is CTM isn't just a little more accurate, it's also better calibrated, meaning its probabilities are more trustworthy, and that's something even humans struggle with here. Happening in figure 11 and 12. The researchers tested that CTM against humans and other models on CIFAR 10. A dataset of small pictures, they group the images by how difficult they are. Think of it like a stool test question. Some are easy, some are really tricky. Now, figure 11.a shows accuracy as difficulty increases. Notice how all models, humans, feed-forward networks, LSTM, and CTM drop as questions gets harder. But the CTM curves, that's the blue one, is the closest to the human curve, that's the green one. That means the CTM behaves most like people as the task gets harder. Now figure 11b and C goes deeper. They measures uncertainty. For humans, they use reaction time. If it takes longer to answer, you are less sure. For models, they use equation based on entropy. That's the equation C equals to 1 minus entropy. That's the softmax of YT upon log C. We have used this in section 2 in the listing 4. This is a fancy way of saying if the model prediction is spread across many classes, it's unsure. If one class dominates, it's confident. Now, look at all the lines. The CTM uncertainty curves matches human closely while the LSTM drifts a bit. This means CTM doesn't just give like a machine, it hesitates like a human when things get stuck. Figure 12 is super cool. It shows the actual neuron activity over time. On the left, CTM neurons wiggle in rich color and diverse ways. Some even show rhythmic patterns. On the right, LSTM neurons look much more flat and negative. This proves CTM's special ingredients, neural-level models and synchronizations, create more brain-like dynamics. Imagine you are taking a multiple choice questions. On an easy question, you circle the answer right away, high certainty. On a hard question, you slur, hesitate, or maybe flip-flop between answers. That's low certainty. Humans show in reaction time, and CTM show it's an entropy. And if you peek into CTM's brain waves, they are full of lively patterns, unlike the duller traces of a regular LSTM. Now, here the researchers tested what happens when we change the number of neurons. Basically, how wide the brain of model is. At first, when they added more neurons, accuracy went up, but after a point, adding even more neurons made the performance drop. Why? Think of it like a classroom. If you have too low students, you don't get enough ideas. If you have too many, it becomes noisy and harder to manage, unless you give them more timing and training. That's what happened here. The wider models may have started overfitting or simply needed more training to work well. To check diversity, they measured something called cosine similarity, which is just a way of checking two neurons are behaving the same. If similarity is close to zero, that means the neurons are acting differently, which is good, but it means each neuron is bringing a unique data. In the graphs, we see that wider models have more neurons acting differently, which means more diversity. So more neurons gave more variety, but after a point, the models couldn't use the variety properly in the limited training time. So cosine similarity is just another that says how similar two signals are. Like example, imagine two kids humming. If they hum like exactly the same tune, similarity is 1. If one hums up and the other hums down, similarity is -1. And if they hums completely unrelated tunes, similarity is 0. In CTM, each neuron has its own tune over time. A score near 0 means neurons are diverse and not copying each other, which is exactly what we want. Now, here where things get interesting. Figure 14 shows what happens when we let the CTM think for more steps. On the left, you see accuracy versus thought steps. Notice how all the accuracies are close, but the models with 50 internal ticks does the best. This struggles that if we let it think more and train it properly, it might get even smarter. On the right, we see something even cooler. When the model feels more certain about an answer, there are two clear points. One is early on and other one is later. That means sometimes the CTM figures things out quickly, and other times if needed to think longer before it's sure. This isn't random, it shows the CTM is following different strategies depending on the data. Just like people, sometimes you instantly know the answer and other times you need to pause and rethink. Imagine you are taking a test. Some questions you answer right away, that's the early certainty pick, and but for louder ones, you think a little longer before writing the answers. That's the later certainty peak. The CTM is doing the same thing, deciding how much time is needed before it's confident. Now, let's see how the CTM handles sorting, arranging numbers in order. This task is interesting because it lets us peek into whether the model is actually following our internal algorithm step by step or not. Here the CTM is asked to sort 30 random numbers. Unlike before, it doesn't even use attention. It just takes a shuffle number directly. At each internal tick, it outputs part of the sequence until the whole list is sorted. Look at the figure 15a. On the x-axis, we have the sequence index, basically which item is in the sorted list we are at. On the y-axis, we have the wait time, or like how many thought ticks the CTM spends before producing the output. Notice the pattern. The model waits longer at the very beginning, gets faster in the middle, and slows down a bit near the end. Figure 15b shows something even cooler. The x-axis here is the data delta, how different the current number is from the last one. The y-axis is still wait time. We can see that when the jump between the number is bigger, the model tends to wait longer before outputting. In other words, the CTM behaves depends on the layout of the data, like it's reasoning about the gaps between numbers. Now, think of organizing books by height. If the next book is close in size, you place it quickly, but if it's much taller or shorter, you pause to think before placing it. In figure 15c, we see how well the CTM generalizes. It was trained on numbers drawn from one type of normal distribution, but tested on distributions with different splits. And look, it still starts them well across a wide range, proving the method isn't overfitted to just one dataset. Now, figure 16 just gives a most detailed demonstration. Each verified color line is one of the number to be sorted. The red bars means the CTM waited longer than average at this time, and the green bars means it was faster. Notice how the longer wait line up with the bigger jumps like between numbers, exactly what we saw in figure 15b. It's like playing a song on piano. If two notes are closed, you move your fingers quickly, but if they are far apart, you take longer to jump between them. So in sorting, we clearly see the CTMs following an internal algorithm. It adjusts how long it thinks depending on the position in the list and the size of the gap, just like how a human would approach a problem. Let's look at one of the most interesting tasks, the parity task. This is like asking the model to read a sequence of 64 numbers, each either plus 1 or minus 1, and at every step say whether the total so far is positive or negative. Humans could do this by keeping a running score in their head, but can a neural network learn to do that? Here's what the results show. The CTMs get better as it gives more time to think, more internal ticks. In these training curves, the CTMs with 75 or 100 ticks can reach almost 100% accuracy. In contrast, the LLM LSTM struggles. Even the best LSTM only reaches around 67% of accuracy, and with more ticks, it actually becomes unstable. It's like giving a student extra minutes on a test. The CTM uses that time wisely, checking more carefully and improving its answers. The LSTM, on the other hand, just get confused if you let you think longer. But now let's take a look into this figure 19. Accuracy alone isn't the most exciting part. The CTM actually learns a sequential algorithm. Now, early in training, it gets the first few positions correct, the early elements in the sequence. As training goes on, it pushes further and further and down the line, learning to predict later and later positions. With 10 ticks, it gets about half the sequence. With 25 ticks, more. With 75 ticks, it gets the entire sequence right. Now, how does CTM actually solve this? By looking at the attention pairs. We can see different strategies emerge. In figure 20, with 100 ticks, the CTM reads the sequence from start to finish, updating its certainty along the way. With 75 ticks, it does something different. It actually works backwards, attending from the end of the sequence, and then makes the confident decisions all at once, at the final tick. This is fascinating because it shows that CTMs isn't memorizing, it's planning. It can invent different strategies to solve the same task. Like think of two students solving a long equation. One works left to right, carefully updating each steps, planning the final result. And the other works backwards from the end, planning each and every final results. Different strategies, same correct answer. So the key takeaway is the CTMs not only improves with more thinking time, it actually learns to follow an algorithm, even inventing its own strategies, like working backwards. That's sometimes ordinary. Recurrent models like LSTM really struggle with. Now, the top row shows the perfect predictions. On the left in panel A, we see the attention trajectories. Each arrow shows where one of the model's attention heads into looking as it ticks. Notice how the attention moves sequentially through the input data, step by step, just like a person scanning left to right. Different heads specializes. Some only attend to positive values, others only to negative, while some handles both. The middle panel, that's the B, is the model predicted output, and the right, that C, is the ground truth. They match perfectly. Now, the bottom row shows a failure case. Here, the input sequence contained only positive values. The attention hedge shows in panel D still moves across the grid, some even alternating between positive and negative slots, but the model struggles to build the correct cumulative parity. The predicted output in E is wrong compared to the target in F. This highlights an edge case limitations. When the data is too uniform, CTM sometimes fails to keep track record of the parity. So what do we learn from this? CTM attention dynamics are interpretable. You can see how it scans, processes information. It's not always perfect, but it really does follow a process, rather than guessing in one shot. Next comes is CTM, which can actually remember, retrieve, and calculate. Now it's your task to do the research, like why author designed a special task that's Q&A MNIST. So basically I tell, so this test is like whether the CTMs can actually remember, retrieve and calculate. So put it in the comments, like what is the behind the research and examples like I am explaining. I want everything in the comments. Okay. Now, so far we have seen the CTM things step by step on images and sequences. But can it actually interact with the world? That's what this section tests. They drop the CTM into classical reinforcement learning games, balancing a pole in cart pole, swinging a robot arm in Arcobot, and navigating a maze in mini grid 4 rooms. In each game, the agency is only part of the world at a time, so it has to remember past steps to make good decisions. This setup is called partially observable environment. Just like when you are driving in fog, you only see the slice of the road, but you need to recall what's behind you to steer correctly. How does it work? Each observation, like the car's position or the robot's angle, is first passed through a few layers of make features. Then the CTM processes those features for one or more internal ticks, building up neuron dynamics. Before outputting any action, this action changes the environment: move left, swing up, or step forward. The loop continues: observe, think for a few ticks, act. Importantly, the CTM carries its internal state across time. So previous moves influences the next ones, just like memory in our brains. So, what happened? Figure 27 shows the learning curves. The CTMs performs about the same as LSTM baselines in all tasks, sometimes a bit better, sometimes equal. That's important. It proves CTMs can handle real-time decision making just like standard recurrent models. But here's the cool part. When we look inside at the neuron activity in the figure 28, we see that CTM developers are richer, more diverse dynamics than LSTM. In Cartoon and Arcobot, both models show simple oscillations, like nervous rocking back and forth with the cart or time. But in mini-grid navigation, CTM neurons show much more complex patterns, while LSTM looks repetitive. That complexity is a sign that CTMs is building a more detailed internal representation of the world. Think about it as like imagine two kids learning to play basketball. Both can dribble and shoot. One just repeats the same steps, simple moves over and over, and that's like LSTM. The other one experiments crossovers, flakes, and tricks. That's the CTM, developer rich dynamics. Both can score, but one has deeper style of play. This just means every action changes what you see next, which in turn changes your neurons. Like a loop where your choices shapes your thoughts, and your thoughts shapes your next choices. That we have seen how CTMs works, let's put it in the context. Section 11 is of the paper is about related works. How CTMs connects to past ideas in AI and how it differs. We will break this into three parts: adaptive computations, iterative reasoning, and biologically inspired dynamics. Most neural networks today use a fixed number of steps, same effort whether the input is easy or hard, but brains and now CTMs don't work that way. They adapt their compute. Earlier works explored this too. Another strand of work is about giving models the ability to reason step by step, like thinking through a problem instead of spitting an answer instantly. CTM is part of this family, but with its own twist. CTM doesn't just loop over same state, it builds a whole synchronization based representation of how neurons fire together over time. Finally, CTM is inspired by brain, not in a literal biophysics way, but in spirit. Real neurons are messy biological instruments. CTMs takes inspiration from them, rhythm and timing, but builds a cleaner, learnable version that fits modern AI training. So in short, CTMs builds on ideas from adaptive compute, iterative reasoning, and brain-inspired models, but its unique contribution is using neural synchronization as the core representation, unfolding through step-by-step or interrupt timeline. Okay, so what did we learn? The author shows the CTM is a brand new way of thinking in AI. It doesn't just pass information forward like user models, it actually uses timing and synchronization between neurons as the core ingredients. That's never been done at this scale before. The idea is neurons keep firing over time, they sync up in patterns, and the model uses through patterns, not just single snapshots to make predictions. This is closer to how real brain works. So, what does the researchers actually find? The CTM is like giving AI a brain that doesn't just spit out numbers instantly, it thinks step by step. Instead of using the same simple activation function like ReLU, each neuron has its own brain and they all synchronize like instruments in a hand. This makes the model more flexible, better at solving problems like mazes, sorting, or image classifications, and even lets you decide when to stop thinking if the task is easy. But there's a catch. The CTMs works by thinking in steps one after another. That means it can't easily be sped up in parallel, like most deep learning models. So it takes longer to train. Also because each neuron has its own tiny brain, the model uses more parameters than usual. Think of it like 1,000 detective instead of 100. More powerful but also more expensive. Okay, so now, this gets you the whole detailed idea of what the paper is and what the CTMs are. So I will end this video now and I will meet you in the next one. Hope you like it and thank you.